We will continue our discussion on the NAND flash. So today we are going to talk about the multi-level cell operation and then the reliability challenges. So in the last lecture, we talked about the NOR versus NAND. And from now on, we will focus on the NAND because this is the mainstream technology. So here, to increase the density of the NAND flash, we can use this multi-level cell operation. So what does that mean? That means in one flash transistor, we are going to store more than 1 bit data. So used to be flash transistor, then you have the electrons, or you do not have electrons, then you have the data 1 and 0. So here the goal is to further increase the density. Instead of storing data only 0 and 1, we want to store data 0, 0, 0, 1, 1, 0, and 1, 1. Using the same transistor structure. So here, the idea is to program the threshold voltage into multi-level states, right? Because here, if you recall, the IDVG, right, of the flash transistor, we have the program states, and then the erased states. So we have this VTH. So the VTH is an indicator of the state. And then the idea is to insert more levels in between so we can create intermediate states. Then we can encode the data into 4 levels. That means 2 bits. Then here the key idea is to inject different number of electrons into the floating gates, right? Because here you have electrons into the floating gates, but the number of electrons will determine the VTH shift. If you have more electrons in the floating gates, you can expect that higher the threshold voltage. So then you can modulate the number of electrons to fine-tune the threshold voltage. So that's the key idea behind the multi-level cell. So here, typically the erased state has negative VTH, like this one, the erased states. And then program states can have multi-level intermediate levels as those. So here then we are going to look at the distribution of those threshold voltage because there will be variations from device to device or from the cycle to cycle. So each VTH actually will become a distribution here, right? Because you cannot precisely program it due to the variation from the device to device or from, let's say, this programming cycle to the next programming cycle. So statistically, if you measure from many samples or from many cycles, then you get a distribution of the VT. So here, that's why we show this VT distribution. And then this is like a probability or number of cells in the measurement. So conventionally, we only have single level cell, right? So here, this erased state or this program state. So we have distribution. So as long as we have the gap between the tails of the distribution, then we can distinguish the states. So here your read condition will be somewhere here, read voltage, right? Then you can distinguish the states. And then we pass voltage. We discussed that in the last lecture. For the read condition, you have to bias those transistors in series, which are unselected, with this V pass R, because you don't know which the state the device is. So you have to assume it's in the program state. Then you can still turn on that transistor. So here we can insert more levels, right? So if we make those distribution into 4 levels, then we can have 2 bits per cell. And typically this is called the multi-level cell. And then here you can have different ways to do the encoding. So you do not want to do the naive encoding. So that means if you do naive encoding, you may think this is highest level or the most program state, 0, 0. Then this is a kind of a next program state, 0, 1. Then this is 1, 0. Then this is 1, 1. So if you do this naive encoding, then this is not the best way. Because here, if you have any error between those two states, right, you're going to generate 2-bit error, because here 0, if let's say somehow there's a shift, then this 0, 1 become 1, 0. So when you read out the data, you get 2-bit error. This is not so good. So that's why you want to switch the order of the encoding. So here, for example, if you have 1, 1, 0, 1, 0, 0, and 1, 0, like this, then you will see that between the adjacent levels, you only have 1 bit difference. So that means if you have an error, you will only generate 1 bit error, right? You can check between those two, only 1 bit difference. So that means the Hamming distance is always 1 between the adjacent levels. And here we can call this MSB and LSB, right? So the first bit is the most significant bits, and then the second bit is the least significant bits. Okay, so this is 2 bits per cell. And then people are aggressive. We want to do 3 bits per cell. That means we have to design this for 8 levels. So that means we have to further split the entire distribution into 8 levels. And then you can do this kind of encoding. You can check the adjacent levels differ only by 1 bit. So then MSB and the central SB and then LSB. So here, as you can tell, as you insert more and more levels in between, then it becomes more and more challenging, right? Because in total, the memory window, that means the lowest level to the highest level, this memory window is not like as large as you wish, right? So typically for the NAND flash, the memory window like 8 volts from the lowest to the highest. So you need to insert 8 levels in between. That means from, let's say, peak to peak, only 1 volt distance, right? In terms of the, if this is 8 volts, then from here to here, roughly speaking, you only have 1 volt margin. But then you have to account for the tail of this distribution. So then the tail, the gap, become very small. Because typically for each distribution, you have a few hundred millivolts, like a spread in terms of the distribution. So it's very difficult. You have to do a lot of verification. We'll talk about that in the next few slides. But the point is that it will become more and more challenging to insert more levels. So then if you do this 3 bit per cell, then this is called triple level cell and TLC for that. And nowadays, QLC is also in product. And that is 4 bit per cell quadruple. And there are some research paper even talk about PLC peta level cell. That is 5 bit per cell. But this is not widely on the market. There's still some like research. And then I even see research paper talk about the HLC. Can you guess what is H? Hexagonal, 6 bit per cell. For example, I remember there was a paper from Toshiba or let's say Kyosha. They demonstrated this 6 bit per cell at a cryogenic temperature, that like 77 Kelvin at no temperature, because the noise and all those variation got suppressed. So they managed to get 6 bit per cell. So this is not a linear increase, because every time when you double this, actually you're going to double the number of levels. 6 bit per cell, that means 32 levels. Actually, no, more than that. 4 bit per cell is already 16, and 5 bit is 32, and 6 bit will be 64. So crazy. But on the market, mostly nowadays, the most product you buy from the market will be TLC and QLC. Okay. So any questions here? So then sensing for the SLAC and the MLC, or in general, multi-bit per cell. So because IDVG will have this kind of IV characteristics, what you want to do is to insert some reference cell or reference current in between, and then you are going to read the cell from here and compare the currents. And then, of course, if you need to do this multi-level sensing, you need to have multiple reference, and then you need to do it multiple times, depending on the sensing scheme. You may need to do it, compare it with multiple references, like a binary tree search, right? You have to first detect whether this device, this particular state, is above this, let's say, this middle one. If it's above the middle one, then you determine whether it is above this one, so you can determine which is which. Okay. So the sensing become more complicated as well. So here, how do you do the programming exactly for this multi-level cell? So you have to play with the programming condition. That means the programming voltage, amplitude, and also the programming pulse width. So here we show some data from some older technologies, but the principle applies even to today's most advanced technology. So here we always erase, if you recall, the NAND flash erase is done by block, right? The entire block will be erased. So you start with the erased voltage, as I said earlier, typically a negative threshold voltage, like negative 2 volts. And then you apply programming voltage. Here you have different voltage from 17, 18 to 19 volts. And then depending on the pulse width, right? So here the amplitude, like for example, 17 volts. And then what is the pulse width? For example, here, this one probably is like a little bit larger than 10 microseconds. So if you apply one pulse, then you change this a little bit, because this pulse width and pulse amplitude is relatively small. But as you further increase the pulse width, if you fix the voltage, if you further increase the pulse width, right, then you are going to gradually ramp up the threshold voltage, because you are going to inject more and more electrons, right? This is effluent tunneling from the substrate or the channel to the gate. So you are going to inject more and more electrons, then the threshold voltage will gradually increase. Of course, you can also play with the amplitude. If you want to do this faster, then you will apply 19 volt, for example, then you can jump this faster. So depending on your target, then you may want to, stop somewhere in this programming. So, but this is not very easy because due to the device variations. So it's not every time when you apply this condition, like 17 volts, 10 microseconds, you always end up here. It may overjump here and here from device to device, or even for the same device this time and next time, then there's a variation. That's why we have this distribution, right? So because we have this multi-level, even TLC, QLC, we have to tighten the distribution. So you have to make it very precise because the margin is so small. You cannot span this, let's say you with like 1 volt to 2 volt, you cannot have this kind of variation after programming. So you have to tighten it. So that's why here, this ISPP is widely used in the practice. So ISPP is incremental step pulse programming, ISPP. So the idea is to first, after each programming pulse, you have to verify. Okay, you have to read to check if your threshold voltage reaches the target or not, because you know the target, right? Here, first, you already decide if you do MLC or TLC, you know the target value, and you know the allowed, let's say the distribution or the spread or the sigma, let's say. So you know the targets and the range. So then you have to program it and then read it and then determine the threshold voltage whether you reach the target or not. If not, then you continue next programming. So here, to make it more effective, you want to ramp up the pulse amplitude. So that's why you will fix the pulse width, but here generally you are going to ramp up the programming voltage step by step. So that's why it's called incremental step pulse programming. So here are some data. You can see that. So this is a distribution you want to target around, let's say, this around 1.1 volts, and then you can have some variation around that. And then here, if you do nothing, let's say you use a constant programming voltage, like 18 volts, then this is the distribution you are going to end up with. So the sigma is like, the span will be like more than 1.5 volts. If you just use the same pulse width, but keep doing the pulsing. So this is not good. But then if you do the ISPP, so you start with some lower voltage, for example, maybe 16 volts, and gradually ramp up, then you will tighten the distribution, okay? Because you prevent this over programming. Because here, if you with a constant voltage, right, sometimes in the first step, you already overshoot your targets. But with the ISPP, you start with lower value, you gradually approach the targets. So then this is easier to get the targets. And here it says that this also reduces the number of program and verify cycle. So here, if you do the ISPP, then you may need 2 to 6 program and verify cycle to reach this particular distribution. And in total, you are going to spend like 100 microseconds to do that. And then if you always use a small voltage, actually you can get even better distribution here. Because you always use a small voltage, let's say 16.5 volts. Then you gradually move this target and move the your value in very small step. You can even get better results. However, to reach this kind of distribution, you need to spend like more than 30 program and verify cycle, because every time you move a little bit, if you don't ramp up the voltage, if you use a very constant small voltage, then you may wait for a long time. So that's why here the ISPP provides a good trade-off between the programming speed and then the final distribution of the threshold voltage. So that's why it's widely used for today's NAND flash programming, especially for the multi-level states. So here, I will talk about how to do the multi-level programming and especially TLC programming sequence. This may also apply for the QLC. So actually, it's not that straightforward, especially when you do the TLC. So here, if we do the MLC, what you are going to do is first, okay, programming the LSB. Some devices, if the LSB, you need to program it, then you are going to split from the erased state. Some of them you will program to some intermediate. This is intermediate step. You are not going to program this to your desired target right away. So you are going to split the distribution like this, okay? And then you split from here to here. So this is better than you directly jump from this 1 to this 4 in terms of the distribution. And similarly for the TLC, this is a so-called the foggy fan programming scheme. So you will do this binary split first, and then from this one you are going to split into 4. But with the coarse grain, the foggy program basically is a coarse grain coarse. So you are not going to fine tune it. You just make some rough, distribution without too many verify cycle. Just get the first initial distribution. And after that, then you fine tune it, fine programming with smaller step, smaller incremental step, and then you do the fine tuning. So it involves a lot of sequences here. That's why you look at the speed here. As I said earlier, so the NAND programming is by page, right? Row by row. So you're going to program the entire row. If you do SLC, you can finish this within like 100 microseconds. But if you do the MLC and TLC, you spend a few hundred microseconds because you have to do a lot of this verify and fine tune. And for QLC, it's even slower, like more than millisecond per page. So you see the trade-off. You get higher density, but then you get slower speed, right? Like your SSD, the capacity become larger, but then slower. So this is a trade-off because you have to do this read and verify. Any questions here? Okay. So then let's move on to the reliability issues. So by the way, before we move on to that, so that's why today's majority, as I said earlier, majority of the SSD on the market is TLC and QLC because you care about the capacity and also the cost. But still, there is a product line based on the SLC. If you are targeting at very high performance SSD, for example, Samsung has this product called Z-NAND. So that is based on the SLC that provide very fast speed, programming speed, even close to like let's say 1 to 3 microseconds very fast, but based on SLC. So this, if you read the tech news of this industry, there was actually also at the very beginning of the semester, I talked about the storage class memory, right? People try to bridge the gap between the DRAM and then the NAND flash. And then, for example, companies like Micron and Intel announced the product based on the 3DX points, which we are going to discuss later in the phase change memory section. So that product failed. One reason of that is because it has a competitor like this one. This ZNAND. Speed is approaching that 3DX point, this Optane SSD. So they are in the same market, but then the NAND flash, of course, I mean, it's more mature and lower cost. And then, yeah, you see what happened in the industry. So it's a tough business there. And for the NAND technology, if you tailor or customize this for particular application, then you can easily kill the newcomers in that field. Okay. Reliability. So the flash memory suffer from the reliability issues. This is unlike the SRAM or the DRAM, because in SRAM, DRAM, we do not talk too much about the reliability. The SRAM, the threat to the SRAM, for example, is a soft error by the radiation effect. But we didn't talk about like endurance, retention, and so on. And for DRAM, maybe the leakage, and you know, the data retention. But then we do not talk about the endurance. So here, those challenges like endurance, retention, program rate disturb mostly happen in non-volatile memory. And flash, of course, is one of the non-volatile memories. So, but later, when we talk about the other emerging non-volatile memory, like RAM, phase change, and so on, they all suffer from these reliability issues, okay? So let's define the reliability problems first in the NAND flash, but this will later apply to other non-volatile memories as well. So first, endurance. How many cycles one can program and erase before the memory window? That means the VTH window collapse. So basically, the endurance is mostly related to the number of write cycles. Number of writes. You cannot write the cell for many, many times. Or in NAND flash, program and erase has one cycle. You cannot do it for many, many times. 1, 0, 0, 1, you cannot switch for a long time. And then retention means how long you can store the charges in the floating gates while maintaining the memory window. So how long this 1 or 0 will stay there, especially at high temperature. So this one, especially at high temperature, like 85 degrees Celsius. That is a typical commercial product industry. I mean, commercial product temperature requirements. Your product needs to be reliable at 85 degrees C. And then if you look at other applications, because there are different grade of the products. If it's commercial grade for the electronics, 85 degree. And then if you look at the other one, like the industrial application, I remember it's like 125 around that. And then the even higher grade is automotive, okay, under your engine hood. That one probably like 150 degrees C. So your data retention needs to be satisfying at those temperatures, depending on your application. So also the NAND flash has this program rate disturb issue. We already briefly talked about that earlier when we talked about the program erase schemes. So basically, when you program or read the selected cell, but the neighboring cells VTH might shift. So that is the disturb. Okay. All right, so then let's look at endurance degradation first. So how many cycles can you write? So here, this is from some older data. So for the 2D NAND in older technology node, but this trend is general. So here we typically show the PE cycles, program and erase cycles, P and E as one cycle. So here then, for this SLC operation, you have program states and erase states. So over the cycling, you keep doing program and erase, and then you measure the VTH, and then you see that gradually the erase states VTH will increase. So here you keep the same programming condition. You are not going to change the pulse width or pulse amplitude for the programming. You are going to use the same programming condition. So you see that then the VTH increase. So that is because over the cycling, you are going to inject the electrons into the floating gates, but some of them may be trapped into the ternal oxide. So for example here, you will have some electrons trapped into the ternal oxide or at some interface trap sites. So if there's trap and those trap cannot release after the erase, then the VTH will be higher, right? Ideally, you want to erase all the electrons from the floating gates, but some of them get trapped, for example, at the interface or at this ternal oxide, then you cannot completely remove the electrons, so the VTH increase, okay? So eventually, then this may, close the window, especially if you think about the multi-level operation, right? So you are going to have less margin between the levels. So this kind of shift will lead to the error. And this typically will be hard error at the end of the cycling. Hard error means you cannot recover. So the device is basically dead. There's no way to recover it. So here, let me see. Another practical suggestion when you do this measurement, it's impossible to read at every cycling point. That means if you do this 10 to the power 6 cycles, that's 1 million cycles. So you can do the pulse programming pretty fast because this is like, tens of microseconds or 100 microseconds. Even if you do 10 to the power 6 cycles, if you do continuous pulsing, right? So let's say if it's 10 microseconds, 10 to the power 6, if you do continuous pulsing, it's just 10 seconds, then that's done. But then once you do the read, you break that continuous pulsing. If you do the read, then you're going to switch the equipment and then do that. If you do the switch between the pulsing mode to the, let's say, read mode, then due to the switch of your readout mechanism, even if you do it every cycle, that will take forever because every switch between the pulsing to the read, let's say you take 1 second. If you measure that for every cycle, 10 to the power 6 seconds will be like 1 month already. So practically, you cannot do that. So what you typically do is to, do many pulsing and then read once. Many pulsing and read once. You just monitor the overall trend, okay? So typically when you do this kind of plotting, you do log scale. And this is also what I told for my students when they write a paper, they have to do this, okay? So you do log scale. You read at every, let's say 10, 100, but you want to add a few more points in between. Typically, I would suggest you do 10 20, 50, 100, 200, 500, 500, and 1000. Okay, you do this kind of points along this log scale. Okay, and then you plot the trend. This is also typically done in the literature. So here, retention. Okay, so the retention actually will couple with the cycling, especially post-cycling retention will be more challenging. So here, the retention is mostly due to, let's say, for the program state, you have electrons in the floating gates, but then some of them, after cycling, some of the electrons, as I said, will be trapped to the ternal oxide. But at high temperature, after baking, those could be released from those trap sites. So that means your data will shift as a function of the temperature. Not only this one, those ones, but also electrons from the floating gate may also jump out because they have, collected energy from the thermal. If you have higher temperature, then they may, this is a barrier, right? Essentially, it's a barrier, and those electrons may jump over. So then the VTH will shift basically, right? Because VTH essentially is number of electrons in the floating gate. As you have fluctuation of those number of electrons, you have shift. So here, for example, some band diagram, this is the electron detrapping essentially, right? So ternal oxide, you may have some trapped electrons, but after baking, those electrons will jump out. So here, if you look at the distribution shift, then you will notice, okay, there will be this kind of general trend for the multi-level cell, let's say MLC. So initially, you may have this distribution, but after the baking, and then you will remeasure the distribution, then you will see a shift from the array. So here we can, let's understand what happens here. For example, for the program state, actually you see in general, even for the erased states after the cycling, because some of the electrons, as I said, still stay in the trap site, so it's not fully released. So in general, you will see the median value of the distribution shift to the left. Why is that? Because you will get electrons, jumping out. Then lower threshold voltage, right? So the distribution shift to the left. This is due to the at high temperature detrapping. However, there's another mechanism to remove the electron that is caused by this SILC. This is called the stress-induced leakage current. So basically, after cycling, you will damage somehow the ternal oxide. There will be the traps. Those traps will assist the tunneling. So it's called trap-assisted tunneling. So it's like a stepstone for the electrons to, tunnel through. This is not thermal. This is quantum tunneling. But the quantum tunneling depending on the barrier distance, barrier height and barrier distance. But if you have some defect in between, then it's like a distance. It's like two-step instead of one-step tunneling, become two-step, and each step is much smaller. But the quantum tunneling rate exponentially depends on the distance. So if you make the stepstone, then these electrons will easily go out. Especially at high field, right? When you have this electric field, then you bend the band, then you have this kind of trap-assisted tunneling. So this trap-assisted tunneling depends on the field direction, right? If it's let's say on the positive side, then when you read it, then actually you are going to detrap. This is a detrap. But then on the erased state, because you are going to apply positive voltage, you are going to trap it again. Okay, because this can go the other way, right? Depending on the voltage you apply. So that's why here you see the tail actually shift to different direction. Okay. So that's different mechanism here. One is the thermal, one is this tunneling. Okay. So any questions here? So in practice, if you want to evaluate the data retention, you have to do this temperature acceleration test. This also applies to other non-volatile memory. We are going to discuss later, like RRAM, phase change, or whatever. Because at the room temperature, this degradation is very slow. You cannot wait for 10 years to evaluate your product. You have to speed up the testing. So typically, we bake at very high temperature, higher than your operational temperature. So here in this example, we are going to bake this NAND flash at 3 temperatures, like 200 degrees C, 250, and 300 for the program states. And then you are going to monitor the threshold voltage shift over the time. So here you're going to define the failure criterion, right? Because this is a gradual shift, and then due to the margin, because here you may have another level here, right? You have this level distribution, and then another level. You know the gap, and then the margin. Then you define the criterion for the failure. So if the threshold voltage degrade to here, then you record the time. This is a time to failure. Time to failure. So you have to do this at different temperature, okay, to record a different time to failure. And then after that, we do this Arrhenius plot, 1/KT plot. So what is that? Because here the assumption is that this degradation is caused by the thermal effects. So all the thermal effects, you have this exponential term, KT over, EA over KT. So all the thermal process is activated by this exponential function. So EA is the activation energy. And then KT is the thermal energy. So here I have to emphasize here the T, you must use Kelvin, okay? You cannot use the degree C. If you use degree C, then your calculation will be wrong. So I think you will have some homework or maybe exam questions on this. I don't know if it's a NAND flash. If it's not NAND flash, then later in some non-volatile memory, like RRAM phase change, it's the same thing. So here, K is a Boltzmann constant, okay? T is a Kelvin. So you know KT at the room temperature is 0.26, 0.026, or let's say 26 millivolts, or 26 milli eV electron volts. Or KT over Q, the thermal voltage will be 26 millivolts. If it's KT thermal energy, it will be 26 milli electron volts. Okay. So here, if you convert to the SI unit, you have to multiply by E, which is the Q one charge quantity. That is 1.6 times 10 to minus 19 Coulomb. Okay. So anyway, you deal with those calculations. I will not spend time to talk about that. But my point is that here, if you plot, let's say, the log scale of this time to failure, if you take the log, and then if you plot the log time to the failure as y, and then you plot 1 over kT in the unit of 1 over electron volts, then you get straight line. And the slope here is the EA. The slope is the EA. You can extrapolate the EA from this plot. So here you get three points. Then you have to plot that 3 points. 3 points. Right, you have 3 failure time to failure at 3 different temperature, but you have to convert the temperature into the 1 over kT. And because it's 1 over kT, actually higher temperature will be lower 1 over kT. So that means this one corresponds to your 300 C, and this one is your 250 C, and this one is your 200 C. And then you do the extrapolation. Okay, this is a standard way. Even in industry, you have to do this. There's no way for you to wait for 10 years to evaluate your product. But you have to do this extrapolation, and then say after 10 years, okay, what is the operational temperature that is still safe, right? So in this example here, okay, if you draw 1 over kT, but then back convert to the degree C, then you see that here is a little bit less than 150 degrees C in this particular example. And then you have to repeat this for post-cycling retention. So here it shows the data for the first 10 cycles. That means you only write 10 times to the device. It's more like a fresh device. But then as you use the device, as time goes by, it's like post-cycling. So after 10 to the power 6 cycles, if you remeasure this retention, that will become the second line here, which degrades from the initial one. So if initially you can be safe for 140 degrees C, now you are only going to be safe for 115 or 114 C, right? Okay, so this is a standard method to evaluate the retention. This also applies to other memories, other non-volatile memories. You will have homework or exam on this for sure. Okay, so we see the trade-offs between endurance and retention. You see that after the cycling, the retention actually become worse. So here, we cannot really require the device to be both reliable in the cycling and data retention. So typically there will be a trade-off. For example, here, the fresh device, if you only cycle it for 10% of the lifetime, then you wish the device could store the data for 10 years long. But if the device is used many, many times towards the end of the cycling lifetime, the data retention may drop to 1 year. So what is the typical, number for the, let me see, do I have that? No, okay. So then I will verbally just discuss that. So do you know what is the typical cycling endurance number for today's NAND flash product? So here, actually, I show some number here. This is for SLC, 2-level, 2D NAND. You can go to like 10 to the power 5 or 10 to the power 6 cycles. Okay. But as I said, majority of the products today is like this TLC, QLC stuff. Then the typical endurance number is this one. No more than 10 to the power 4. Even less than 1, if it's QLC, for sure it's less than 1,000 cycles. You cannot use it for for a long time. Of course, you have enough space. You can trade off that, right? You have your 1 terabyte. You don't need to write 1 terabyte for 1,000 cycles, right? So question? So this one, even at high temperature, you want to have like 1,000 cycles. This is a typical number, okay? For today's MLC, TLC, so on. Even QLC, maybe even less than 1,000 cycle. And data retention, the typical requirement for the SLC is 10 year at 85 degree. We're talking about the commercial application. But you know, for the TLC and QLC, this may degrade to 3 year at 85 degrees C. Right, because they may assume that you are going to change your phone every 3 years. You don't need to keep your data for a long time. So the reliability standard degrades. Of course, for particular applications, if it's like a automotive, then you still need a very high standard because you are not going to change your car for 3 years. So depending on your application, okay? And then let's talk about the program disturb. So here, we actually mentioned this before. So for the programming scheme, we will have this inhibition voltage, right? Then this one, for this cell, we hope the channel potential is, you know, raised up. Therefore, here, the programming voltage minus the channel potential, effectively, you do not have large voltage across this gate stack. But if your channel potential somehow is not raised up, then you may have large voltage across on this one. Then this will kind of program this cell, right? So here you rely on the channel inhibition or self-boosting to reduce this voltage. So this, of course, will be under disturb, right? And then this is a program, this is a cell we are going to program, okay? And then this is half select. Share the same word line and also share the same bit line, you will have some half select. Because here this V pass itself is kind of high, right? The V pass, even though here this one is ground, I mean the channel, this 0 voltage is passed to the channel. Then the V pass W itself is kind of high, so you still have certain probability to inject the electrons. So both those two cells may shift the VTH higher. That's why here, if you look at the distribution, if you keep doing this kind of programming, and then the cells tail, especially the tail, will shift to the right because both are under programming disturb. And programming means you are going to kind of program. Program means higher threshold voltage. So that's why here the distribution will shift to the right. But you notice that this will actually affect this erased state more. And here for the multi-level states, those two are actually okay, kind of okay. Why is that? Because here your V pass W is somewhere here, right? Your V pass W. Or let's say the difference between the channel and then the gate voltage. Or let's say your V disturb. So then for this one, because you have no threshold voltage, the effective voltage drop across this state. If this state is in the erased state, you have higher field, right? Higher field. So you are going to inject more electrons. But here for the L3 state, because the threshold voltage is high, so effectively you have less field across this stack. So that's why here you have more disturb in this erased state. So here for the V past W, you have to carefully choose that, right? So here we show some trend. If your V past W is too small, let's say below 10 volts, which one will have problem? If your V past W less than 10 volts, in this case, you see here this one, this red one, the threshold voltage start increasing. Why is that? Why is that? If V past W is kind of small, recall here, if this is kind of small, then this inhibition will not be able to deliver, right? So then if here the channel potential is not high enough, then this cell will have large voltage across that. So on the other hand, if the V past W is too high, then you see the blue cell itself, the V past W, if it's too high, then of course more and more electrons will be injected. So then the VTH will shift. So there's only a small window to operate the V past W. Typically in the middle, right? Here, if the V programming is like 20 volts, then the V past W is somewhere in the middle. Okay, any question? And then rate disturb. Okay, so the rate may also cause some disturb, right? Because you recall we discussed before, the V rate path needs to be higher than the high VTH states. So here, the highest VTH, right? For example, if it's 5 volts, let's say this minus 2 volt to 5 volts. As I said, the typical window will be like 7 volts or 8 volts in total. So this V pass R needs to be larger than that, because you don't know this cell will be 0 or 1, but you want to turn it on regardless the state, because you are going to read this one. So you want all other pass gate transistor in series will be on. So you have to apply 6 volt on this one. Therefore, whether this string will have current or not fully depend on this cell, right? This is your selected cell. If a selected cell is on, then the entire string will have current. If the selected cell is off, then you do not have large current through the string. So you want other cells to be fully on. That's why you apply this V pass R kind of high voltage, 6 volts, for example. So if you keep doing the rate, even though 6 volt kind of small, but if you keep doing that, then there will be some probability to inject some electrons. That means the VTH will shift. So especially for the similarly for this erased state, because here the V pass R is higher than the highest threshold voltage. So effectively, this erased state has the largest voltage drop or field across the stack. So here the probability of the rate error, you see, also depend on the cycling, right? No pre-cycle, fresh device, then you have to read many cycles to get certain probability of the error. But then as you do more and more cycling, here the cycling means the program erase cycling, and then this is let's say PE cycling, and here is a read cycle. This is read cycle. So after you do the PE cycling, for example, then 10K PE cycling, then even you read 10 to the power 5 cycles, you may get like a very small percentage error. Of course, the error rate is low, but you have a large capacity, right? So here, for example, the error rate 1e minus 6. That means one error out of 1 million cells, 1 megabit. But your flash easily you have gigabits. So you still have quite a lot of errors due to this. So that means you have to use error correction and other mechanisms to protect the data. So here is a summary of the distribution of the VTH states due to different reliability challenges, right? So here, just a quick summary. Read disturb, program disturb. Of course, program disturb will be more severe than the read disturb because programming voltage is still much higher than the read voltage. Even the read paths are like 6 volts. Then program disturb voltage could be like 10 volt, even 12 volts. So here, then you will have this tail to shift to the right, especially for the erase states. So program disturb will be more severe. So even for this intermediate state, you will have some trouble. And then the PE endurance cycling, as we showed earlier, mostly because the trapping, you cannot fully erase. So the erase states shift to the right. And then data retention, okay, because of the detrapping, you get the shift back to the left for all the states. And then due to the stress-induced leakage current, this SILC, you have the tail depending on the voltage polarity due to the electron tunneling through those traps. Okay. So here, the last column is last row is this erratic overprogramming. So sometimes, due to the positive charge trap in the peroxide, which effectively reduce the barrier, so the programming electron somehow could easily go through because here this positive charge bend down the band. Then the electrons do not see much barrier, easily it turns through. So that will overprogram it. So here you may have the overprogramming. So typically you have a long tail on this side due to the overprogramming. So that's the reliability challenges for the NAND flash. Any questions? So yeah, pay attention to this distribution, this plot. It's helpful to understand the challenges here. All right, so then we still have like 10 more minutes. So let's continue. Scaling challenges. So here, if you look at the scaling trend for the 2D NAND, if you really look at the minimal pitch, half pitch of the cell, actually the 2D NAND scaling outpace DRAM scaling and logic scaling. So if you want to talk about smallest transistor we ever built, then the 2D NAND is the smallest one. If you look at the pitch of the transistor dimensions, then the 2D NAND without a contact, right, between the source and drain, then the 2D NAND is very small. So it entered to the sub 20 nanometer, close to 10 nanometer region around 2013, 13, 14, and 15. So after that, there's no way to further scale the 2D NAND. So the industry switched to the 3D NAND, and we're going to talk about that later. So there is a shift from the 2D NAND to the 3D NAND. But you need to understand that after we switch to the 3D NAND, the critical dimension, the minimum feature size, actually relax. Okay. The 3D NAND, if you really talk about the F, that will be pinner to pinner. Okay. It's actually larger than 100 nanometer. So horizontally in the XY plane, actually you relax the device dimensions. But you gain the density by stacking more in the vertical dimension. That's how you equivalently scale. Okay. But if you look at the two-dimensional XY feature size, 3D NAND is much larger than the 2D NAND, the last generation of the 2D NAND. I would say the last generation of the 2D NAND is the smallest device that the industry has ever built. Okay. So here, this is a scaling trend again. And in terms of the equivalent cell size, you see the last few generation of the 2D NAND effective cell size. This is all SLC. When we talk about the cell size here, we didn't account for the higher density due to the multi-level operation. So here we just talk about the actual geometry. Okay. So here you see that the last generation is like 100 nanometer square. That means 10 by 10 nanometer, roughly speaking, or maybe 12 nanometer by 12 nanometer in that scale. So that is very small, even smaller than today's logic transistor. So after that, then switch to the 3D. We'll talk about that later. So here you see there are some like key innovations. For example, the multi-level cell was introduced here. And then there's a double patterning, air gap, and so on. We'll talk about that in more details. And here, I think this number is the capacity per die, per chip. So it's a small b, gigabits. So here, then the last generation of the 2D NAND give you about like 128 gigabits per chip. This includes the multi-level cell. Okay, it's not 128 giga transistors, but each transistor, you know, store 2 bits or 3 bits. So effectively, you get more capacity. So then the transition happened around this time, like 2014, 15, 16. And the first generation from Samsung is 24 layers in the 3D, number of layers, like 24, the first generation. And then it went to 32, 64, 128. And today, 24 is 300 layers. We'll talk about that more. But before we talk about the 3D NAND, we need to understand why the 2D NAND cannot scale further. So there are challenges listed in this slide, but I would say there are a few key challenges. The first one is the cell-to-cell interference or cell-to-cell coupling. This is a very significant. So when you are looking at the 2D NAND, so here you have the floating gate and control gate, you share the word line, for example. Then from one floating gate to another floating gate, you have this coupling cap, parasitic cap. So here when you program this cell, then some of the voltage will be capacitively coupled to this floating gate. So you will further disturb this floating gate, the adjacent cell. As you scale, this distance become like 10 nanometer or 12 nanometer or so. So this scaling makes this capacitive coupling very strong. So you cannot really isolate between cells. You program or even read this cell then this voltage will affect other cells' threshold voltage. And also, number of electrons also become a problem, because here the dimension is so small, like 10 nanometer or so. So the number of electrons you can store here, inject here, only maybe a dozen, maybe 20, 30 electrons. So you only, have 20 or 30 electrons. If you lose one electron, you're going to shift the VTH by a few percent, right? You think about this entire spectrum as a window for like 8 volts. If you lose one electron, you're going to move like 500 millivolts. This is crazy. You cannot allow that, right? Because your multi-level cell or TLC will basically corrupt right away if you lose one electron. So those are the challenges. And of course, there are some other fabrication challenges. But I would say the cell-to-cell coupling and then the number of electron, few number of electron, they call few number of electron, is a problem. So yeah, I don't have enough time to finish all of them. So let's stop here today, and we will continue the discussions on Thursday.